When people discuss ideas of how terrestrial Mesozoic vertebrate ecosystems changed over time, the most often brought up examples are the major transitions that exemplified the changes from one period of time to another. Triassic to Jurassic, Jurassic to Cretaceous, and so on. As true as that may be, there were many other smaller transitions of biodiversity in terrestrial ecosystems in between these world-changing transitions that still had quite the impact on the flora and fauna of the time. One of the most mysterious of these relatively smaller changes is the early Cretaceous to the late Cretaceous. This is probably due to a poor fossil record, but could also be from a lack of zealous sampling of these formations. The next most mysterious of these transitions occurred from the beginning to the end of the late Cretaceous epoch, the Campanian to Maastrichtian ages. It's from this more recent transition that interesting conundrums present themselves. The exact evolutionary trajectory of certain animal groups from the beginning of the late Cretaceous to its abrupt end via fireball is still being pieced together as new data is added to the mix. One such piece of data has just been readjusted thanks to the work of scientists rechecking what had been known before, and it promises to make a hell of a lot more sense out of the evolution of one of the most famous dinosaurs ever known, Triceratops. When it comes to dinosaurs and other prehistoric animals, Mexico rarely enters the conversation, but this is changing and has been changing for the last few decades, especially regarding Mexico's late Cretaceous. This improvement of Cretaceous Mexico is due to a series of expeditions led by Mexican institutions and a few conducted in partnership with international researchers. These many expeditions have produced Paracentosaurus, Acantholepon, Totelmimus, Coahuilaceratops, Latyrinus, Huehuecanautlus, Tlatolophus, Velofrons, Magnapolia, Labocania, and Coahuilaceratops. These critters all come from various points of the late Cretaceous and represent slight variations of fauna found throughout the western half of North America, which was the subcontinent Laramidia for much of the late Cretaceous, due to the western interior seaway cutting up the North American continent. Three of the most fossiliferous formations from this time and region are, according to tentative dates, the Turonian 100.5 to 89.8 million-year-old La Bocona Roja Formation of Baja California, the Santonian to Maastrichtian 86.3 to 66 million-year-old El Gallo Formation, also of Baja California, and the Campanian 73.63 to 72.74 million-year-old Cerro del Pueblo Formation of Coahuila. The Cerro del Pueblo has been the one to produce the highest number of critters. A bunch of currently unnamed or unnameable ankylosaur, ceratopsian, ornithopod, and theropod fossils, plus the named Coahuilaceratops, Critosaurus, Latyrinus, Tlatolophus, Velofrons, and Paracentosaurus, and the adorable turtle Mexicheles. The Cerro del Pueblo is also part of a much bigger complex of formations called the Difunta group. This group stretches from the Campanian age of the late Cretaceous to the Paleocene epoch. With so much seemingly known of the Cerro del Pueblo formation, does this imply that equally as much is known of the other geological formations within the Difunta group? No, and as you will learn, even the Cerro del Pueblo has lots to teach. The bottom of the Cerro del Pueblo formation has been and is well studied and understood, but the same cannot be said of the upper layers of this formation or the formations that were laid down on top of it. This is where Coahuilaceratops and the horned dinosaurs come in. Two horned dinosaur specimens, an adult and a juvenile, were discovered in rocks of the Cerro del Pueblo formation in the early 2000s. These fossils wouldn't receive the name Coahuilaceratops until a 2010 paper. Even at this time, Coahuilaceratops was an atypical and exciting example of rare southern North American Chasmosaurine ceratopsians, the big-browed, square-frilled forms. Many more of these critters have been found since, like Navajoceratops, Terminocavis, Sierraceratops, Bisticeratops, Bravoceratops, and a bunch of yet-to-be-named specimens. This has allowed for far more clarity as to how and where these specific types of horned dinosaurs evolved across Laramidia. A brand new study has been published by a huge group of researchers, including Daniela Barrera Guevara, Dr. Belinda Espinosa Chavez, Dr. Claudia Inés Cirano Brañas, Claudio de León Davila, Daniel Posada Martinez, Dr. Elizabeth Friedman Fowler, and Dr. Denver Fowler, in the journal Diversity. They found some unusual inconsistencies about the Coahuilaceratops quarry when revisiting it to collect stratigraphic information as part of a bigger project. The dig site isn't Cerro del Pueblo. So, the rocks in the Coahuilaceratops quarry are a drab beige-colored shale. The rocks of the Cerro del Pueblo formation are also beigey, fine-grained sediments like mudstones and sandstones. The formation above the Cerro del Pueblo is called the Cerro Huerta Formation and is composed mostly of red siltstones. When the authors were inspecting the quarry, they found that the rocks directly above and below the quarry were red siltstones. Uh-oh! In geology, there are many terms that seem like they all mean the same thing. Indeed, there are even terms that change definition depending on which geologist you are talking to. However, there are definitely a majority of terms that have a generally agreed upon definition. To that end, I usually use the word layer to refer to the geological phenomenon that is scientifically named formation, because it paints a good picture as to what something like a formation looks like, a big layer of rock. However, this may indicate that a formation is just one layer, when a formation can be made up of a bunch of very thin rock layers. The way the term layer is used in geology is as a synonym for the term stratum, all of which are words to refer to a single isolated layer of rock that is consistent in lithologic traits, such as color, sediment size, dating, rock type, mineralogy, fabric, texture, and the like. These layers are usually quite thin. A formation is often composed of many of these layers, or strata, that are combined together because of shared traits. There are also many ways to tell formations apart. Formations often have a bunch of different traits: coarse to fine-grained sized sediments, different mineral makeup, fossils, colors, and more. So if one formation, say the Cerro Huerta, is made up almost entirely of red rocks, and the formation right below it, let's say the Cerro del Pueblo, is made up almost entirely of beige rocks, and you have a Cerro del Pueblo dig site of beige rocks sandwiched between red rocks, then this is evidence that the beige dig site really belongs to the red formation rather than the beige formation. This is especially true if that beige formation has absolutely no red rocks, but the red rock formation has occasional occurrences of beige rocks, which in this case is true. Just to be clear, color is quite low on the totem pole of traits used to distinguish formations from one another, but it's used here due to the classification history of these two formations. When a geological formation is first described, there must be a clear diagnosable trait to set it apart from the formations it overlays and underlays. In the early 1960s, when the Cerro del Pueblo and Cerro Huerta were first described, the boundary between them was simply marked as the base of the first red bed. So, this is what sparked the team to do a more thorough investigation of the quarry site rocks. With a little stratigraphic detective work, the team confirmed that the Coahuilaceratops fossils really did originate from the Cerro Huerta formation rather than the Cerro del Pueblo. What's even crazier about this is that the quarry is not even close to the bottom of the Cerro Huerta. There's about 1/3 of a mile of rock below it before the Cerro Huerta becomes the older Cerro del Pueblo. Wild, huh? So, with this new sexy data jumbling in your noodle, what does it all mean? This relayerifying of Coahuilaceratops means that the great horny beast is up to 2.5 million years younger than previously thought, occurring in the early Maastrichtian age of the Late Cretaceous. For the number nerds out there, that's 73 to 72.5 million to 71.5 to 70.5 million years ago. This means a few cool things. 1. This makes a lot more sense for the animal than what was previously thought. You see, Coahuilaceratops brandishes traits that are only found among the later, more advanced Chasmosaurine ceratopsians, critters like the Triceratopsini. These unique traits include a nose horn further forward on the snout, huge brow horns directly above the eyes and incorporated into the eye socket, and some bony bumps along the middle bar of the frill. all things seen in Triceratops. Sure, Coahuilaceratops has moved around in scientific organizations of the Chasmosaur family tree very slightly over the years as new data is added, like any other ceratopsian, but it has remained, more or less, closer to the big-frilled southern Chasmosaurs than anything else. 2. Coahuilaceratops is the first known dinosaur and first diagnosable fossils from the Cerro Formation, and therefore represents a brand new fauna in the Maastrichtian of southern North America to be uncovered down in Mexico. The Cerro proving to be a far more fossiliferous formation than originally thought, makes it a brand new early Maastrichtian formation to dig at, and those are really rare. This could mean a lot more dinosaur fossils are to be found in this formation, a formation that was overlooked for a purported lack of substantial fossils. Or there are now some fossils labeled as Cerro del Pueblo that actually belong to the Cerro 3. This adds fuel to a long-standing hypothesis first proposed by Chasmosaur expert Thomas Lyman in the 1990s and 2000s. The Biogeographical Hypothesis. North America was divided into 3 continents by a shallow inland sea throughout much of the Late Cretaceous: Appalachia to the southeast, Franklinia or North Appalachia to the northeast, and Laramidia to the west. This continental split also split up populations of dinosaurs. The Biogeographical Hypothesis, in this context, posits that dinosaur populations across the western Laramidian landmass were physically divided into northern and southern populations. This hypothesis would find further evidence with the 2020 work of Denver Fowler and Elizabeth Friedman, who found the exact mechanism for this physical division between north and south: the sea. The Western Interior Seaway would widen and narrow over time due to various natural processes, and this would push and pull the margin of the sea towards and away from Laramidia. The movements of the sea, as they are preserved in the rock record, are termed regression, for when the sea retreats from the land, and transgression, for when the sea overtakes the land. An example of physical evidence of this change lies in the strata, or layers of rock, that make up formations and such. Some sediment can only be laid down by actions of the ocean, while others are more common in lakes, rivers, etc. So, when you have terrestrial sediment layers that change to marine and then to swamp and then to terrestrial again, you have a sequence of rocks that prove change of the environment over time. The ocean invaded, retreated, and invaded again. As far as is known, when the edge of the Western Interior Seaway invaded Laramidia, it did not cut all the way through it like it had done to the entirety of North America. Instead, it simply flooded low-lying areas up to the baby Rocky Mountains. Most animals can't traverse huge mountain ranges, so when the ocean cuts off low-elevation areas that would allow animals to move around the mountains, they are stuck in one chunk of the continent. This segregation of animal populations led to different evolutionary paths for the various lineages that had been separated, a process called allopatric speciation. Okay, how does this relate to Coahuilaceratops and the Chasmosaurs? So, in that 2020 Fowler and Friedman paper, they pieced together all the evidence into a timeline that makes sense. The anatomy of the various known Chasmosaurs suggested that the group had split into at least 2 lineages quite early in their development. Then we have that Western Interior Seaway ebb and flow cycle intermittently cutting off and joining the north and south halves of Laramidia. So, that likely means 2 lineages of Chasmosaurian horned dinosaurs were present along the coast of Laramidia from the middle to the late sections of the Campanian age, which is the second to last chunk of the Late Cretaceous from 83 to 72 million years ago. These 2 were a northern Chasmosaurus lineage and a southern Pentaceratops lineage. At around 81.5 million years ago, there is no sea separation, and there's just one continuous strip of Chasmosaurs from north to south. Then, at around 81 million years ago, the sea invades the land and splits north and south populations. This leads to speciation over a few million years, with distinct north and south Chasmosaur populations forming the Chasmosaurus and Pentaceratops lineages. The Chasmosaurus lineage is characterized by square frills and smaller horns, while the Pentaceratops lineage had a heart-shaped frill with a deep indentation in the middle and huge brow horns. We will see how these shapes change over time. Then, at around 76.5 million years ago, the sea says sayonara and joins North and South populations together. This is how we end up with the Albertan Vagoceratops of the northern Chasmosaurus lineage and the unusual occurrence of the also Albertan Chasmosaurus russellii of the southern Pentaceratops lineage. Now, this is a very big taxonomic mess. Chasmosaurus was used as the wastebasket for all sorts of fossils found throughout Canada and surrounding territories for many decades. This is an area of high scientific interest, and a lot of work is to be done with the mess that is the Chasmosaurus genus. So for now, Chasmosaurus russellii, the paper authors are referring to in this diagram, is specimen CMN 8800. Whether or not it will remain Chasmosaurus remains to be seen. Back to the maps. 500,000 years later, the lineages evolve into Cosmoceratops of the Chasmosaurus lineage and Utaceratops of the Pentaceratops lineage. Cosmoceratops is instantly recognizable as being super weird, with a series of spikes that fold down and forward over the frill, plus two moderately long brow horns that bend up, out, and down. Utaceratops, on the other hand, is a lot closer to what you may recall of Pentaceratops. It has a heart-shaped frill with a deep indentation in the middle, which is called an embayment, and short brow horns that bend up and out. Both of these critters are from Utah 76 million years ago. Their co-occurrence is evidence of both lineages migrating north and south, thanks to the sea not blocking the way. Between 75 and 74 million years ago, the sea comes back in and the Chasmosaurus lineage seems to have gone extinct. This is when you get the first occurrence of Pentaceratops proper, and then its evolution into Navajoceratops, and then into Terminocavus. At 73 million years ago, the sea moves away again, and allows the Pentaceratops lineage to colonize the entire range of the Laramidian coast. At this point, the Pentaceratops lineage is the dominant Chasmosaurine lineage. The last currently described definitive example of the southern Pentaceratops lineage is Terminocavus, with the embayment now closing in on itself. Okay, so now I have to interject with the new hypothesis proposed by the time replacement of Coahuilaceratops. Thanks to Coahuilaceratops being much younger than previously thought, the team now suspect that the Pentaceratops lineage went through a split into two other lineages during the end of the Campanian and start of the Maastrichtian ages. Okay, back to the diagram. The new hypothesis proposes this. At about 72.5 million years ago, the sea had split the Pentaceratops lineage in two, with another north and south population that would speciate. A hypothetical proto-Anchiceratops in the north, and Coahuilaceratops in the south. Coahuilaceratops took the Pentaceratops traits and ran with them. The nose horn shifted forward on the face, the brow horns became the largest brow horns known among the ceratopsians, and the middle of the frill gained raised bony bumps. These are traits seen only in the Triceratops lineage, making Coahuilaceratops the first appearance of these features in the Chasmosaur fossil record. At the same time, but north of Coahuilaceratops, other possible branches of this group have been found: the dubious Bravoceratops, the undescribed and unnamed Almond Formation Chasmosaur, and the recently described New Mexican Sierraceratops. Interesting side note, the skull of Coahuilaceratops is not super complete. It contains the important parts of the frill and horns for classification, but there is some wiggle room. Considering what Coahuilaceratops is most closely related to, some of the proportions of its skull should be more Triceratopsian than Pentaceratops-like. That is, a shorter snout and rounder squatter frill, like these images provided in the new paper. From there, at around 71.5 million years ago, the sea goes out again and allows the now distinct groups of Chasmosaurs to mingle. At this time, the southern Pentaceratops lineage is exemplified by a Rhinoceratops, which evolved from Coahuilaceratops-like Chasmosaurians in isolation in the south, while the northern Pentaceratops lineage is exemplified by Anchiceratops. A Rhinoceratops has the middle bumps in the middle of the frill, the big brow horns, and forward-pointing nose horn of Coahuilaceratops. But now the frill holes have started to shrink, and the indentation in the middle of the frill is completely gone. A Rhinoceratops also starts the trend of becoming boring. All of the bony spikes along the frill, called epoccipitals and epiparietals, are the same shape. Anchiceratops, on the other hand, has a pair of frill spikes in the middle of the frill pointing outwards like a butterfly's wings. There is no embayment here, so it's hypothesized these butterfly spikes are vestiges of the spikes along the embayment in earlier Pentaceratops types. From here, it starts getting unusual because the western interior seaway began to move out of North America. This revealed a lot more lowland areas along the coast of Laramidia for chasmosaurs to colonize. This occurred by 68.5 million years ago, with Regaloceratops the last remaining member of the northern Pentaceratops lineage, and the new Triceratops the exemplar of the southern Pentaceratops lineage, that is, by this time, invading the majority of the continent. It becomes the dominant ceratopsian in much of North America. Regaloceratops took the Anchiceratops traits and screwed them up. The butterfly spikes merged into one central spike. All of the rest of the frill spikes are uniform in shape, and it has small frill holes. Triceratops, and perhaps more accurately its Triceratopsine lineage, developed smaller and smaller frill holes until they disappeared entirely in Eotriceratops and Triceratops. This lineage continued with the big brow horns. The nose horn continued to move forward on the snout, and the frill decorations became smaller and less showy. After this point in time, around 68.5 million years ago, Regaloceratops and the northern Pentaceratops lineage fully goes extinct, leaving the new Triceratops lineage to inherit the Earth, though not for long. This new paper lays the foundation for a new understanding of how the later Chasmosaur lineages may have split and diversified throughout the very end of the Cretaceous. However, there are some outliers that present some interesting possibilities for later study, such as Bravoceratops, which may be a dubious dinosaur in and of itself, Spiclipius, Sierraceratops, Bisticeratops, and plenty that are known but have yet to be officially described or published. What did Sierraceratops, Bravoceratops, and/or Bisticeratops' frill look like? Now that the Cerro formation appears to be more fossiliferous than previously thought, it may prove to be a formation potentially rich in remains of dinosaurs and other early Maastrichtian fauna. Furthermore, the possibility exists that other dinosaur fossils may already exist that have also been misidentified as belonging to the Cerro del Pueblo formation. Many exciting things lie in wait for the future of ceratopsian science, and I hope to be the first to cover it for you all. I want to thank the authors for giving me early access to bring this video to you. Special thanks go to paleoartist and paleontologist Daniela Barrera Guevara, as they were extremely helpful in answering all of my questions and providing corrections and helpful suggestions for the script. This was the first paper in which they were lead author. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, like this video, drop a comment in the comment section below, and hit the bell icon to stay in the know with everything Edge. Thanks for watching.